Okay. Hi, everyone. Welcome to the tutorial for deep modeling with long-range electrostatic interactions. In this tutorial, we will do these three exercises to familiar with the DPLR method. And we assume that you are already familiar with DP. So in this exercise, we will focus on explaining the difference between DP and DPLR. You can find these three exercises here in the hands-on sessions, day 2, and this folder. This number 1 to number 3 corresponding to our exercise from number 1 to number 3. And before we go through these exercises, I'd like to mention some basic theory of DPLR. This will help us to understand the input files in our following exercise. In DPLR, the long-range electrostatic interactions is approximated by the distribution of spherical Gaussian charges located at the ionic and electronic sides. So we can know the largest difference between DP and DPLR is we have one-year centroid here, and this one-year centroid is predicted by the deep one-year neural network. Here we will use the deep one-year neural network that we obtained this morning. It's called dipole.pb. And the electrostatic interaction energy is calculated using the Ewald sum. And here we use the fast algorithm for the Ewald sum. It's called particle-particle-particle mesh methods. Now let's see this exercise. First, let's go to the exercise 1. You will see there are two files here. One is the deep one-year model dipole.pb, and one is the import JSON. If you open this JSON file, you will find it's very close to the DP model that the training of the DP model. And the largest difference here is we have another block. Here we should tell it which deep one-year model we want to use. And this is the charge of the one-year centroid. Here we use water as an example. And as you can see here, each water molecule, the one-year centroid corresponds to 4 one-year centers, and each center has a charge of -2. So the total charge will be -8. And this is correspond to the ionic charge. And in our system for water, our ion is the oxygen and hydrogen, and oxygen has a charge point +6, and the hydrogen has a charge +1. And this Ewald beta is this spread parameter for the spherical Gaussian charge. Yeah, and also this Ewald H assigns the grid size of the Fourier transfer because we do the Ewald sum in the Fourier space. And then you can just use dptrain to train a DPLR model. The training will take 20 hours, but in this tutorial, we don't have time to wait for the result. So after some steps, for example, like 1,000 or 2,000 steps, you can just kill the job using Control-Alt-C. Then you can try to freeze your model using DP freeze. But this model haven't been converged. It's just an example. We will provide you with the converged model in the following exercises. The second exercise is compare DP with DPLR. We have introduced this example in the lecture this morning, and in this exercise, we will reproduce this figure. You can go to the water dimer folder here. Sorry. It's here in the folder 5, and here there is a water dimer folder, and you can find 2 folders here. One is data, one is predict. In the data folder, we have the configurations of the water dimer with the distance between 2 oxygen atoms from 2.69 to 10. Then let's go to one folder. Here we have the WASP output file. Let's say the alt car. Here we have the coordinates of the water dimer. A water dimer has 2 water molecules and 6 alkanes. So you will see the coordinates of the 6 alkanes here. And at the end of this file, that is the DFT energy. And then let's go back to the predict folder. You can go to this DPLR, and we use this script to predict the energy and the force using the DPLR model we just obtained and the dipole model. Let's see this file. First, we tell it which model we want to use. Here we use the model.pb. And there are several most important commands. One is the DP data. We tell the code that we want to get the Elton coordinates from the outcar file. We have just seen that. And we can also get the DFT energy from this file using DP data. And we also evaluate this means to predict the energy, force, and variable from our model.pb model. And then we just write the results to an output file. And at the end, you will get file named dplr.data out. The first line is the distance between 2 oxygen atoms. The second line is the energy predicted by our DPLR model. The third column, the third column is energy predicted by DFT. That's extracted from the outcar file. And we have provided you with the DP results, which is without the long range in this folder. And what we want to do is to put all the results in one figure. Here we use the Jupyter notebook, and you can find the results here. You can see that DP DPLR is much closer to DFT than the DP model. The third exercise is using DPLR to conduct molecular dynamic simulations. And we go to the third folder, 3 and D here. You will find 3 files. This one is the DPLR model, and this one is the configuration file. This file has 64 water molecules. It's bulk liquid water, and this is the LAMP import file. First, let's see this configuration file. You can see it has lots of molecules because here we have 64 water molecules. It's too long, so for simplicity here, I only use a system that has 1 water molecule as an example. You can know that 1 water molecule have 3 atoms, 1 oxygen, 2 hydrogen. But here you will find the number of atoms is 4. That's because we have 1-year centroid, because we want to use this 1-year centroid to predict the long-range electrostatic interaction. And at the initial configuration, we don't know the position of this 1-year centroid. So we can assign the position of this 1-year centroid. We call it virtual atom. We can set its position equal to the its corresponding oxygen position, and after the simulation starts, this coordinate will be updated to the coordinates of the 1-year centroid automatically by using the deep 1-year neural network. And we also assign a virtual bond between the oxygen and its 1-year centroid. We can see here the type 1 atom is oxygen, and the type 2 atom is virtual atom. They have a virtual bond. We set this virtual bond because we want to tell the code that this 1-year centroid belongs to this water molecule, not to the other water molecule. If you have lots of water molecule in the system, you should assign each 1-year centroid, the virtual atom, to its corresponding oxygen atom. And finally, let's see the LAMP import file. The largest difference between DP and DPLR here is we have virtual atom, and we first give these atoms a type group. Type 1 and 2 is oxygen and hydrogen. They are the real atom. Type 3 is 1-year centroid. It's a virtual atom. And we use the model.pb that stores both 1-year centroid, the deep 1-year and DPLR models. So the position of the 1-year centroid and the energy can be inferred from this model. And you can see a virtual bond is specified by bond type 0 because we only want to use the virtual atom to predict the long-range electrostatic interaction. We don't want the virtual atom to interact with other atoms in the system. So we use this command to switch off the interaction between real and virtual atoms. And this long-range part is calculated by the case-based style, PPPM, because we used the particle-particle mesh method to calculate this Ewald sum. And here, beta is the spread parameter for the spherical Gaussian charge. It should be set to be the same as that we used in the training in the exercise 1. And this K-mesh should be set dense enough so the long-range calculation is converged. My experience is that to set this K-mesh equal to twice of your box length in angstrom. And then we use fixed DPLR to calculate the position of the 1-year centroid. by the deep one-year neural network and back propagates the long-range interaction on the virtual atom to the real atom. And also, if we want to do NPT simulation, we want to control the temperature and pressure on the real atom, not to include the virtual atom. So we should add compute real temperature, and it's computed on the real atom because we have defined the group real atom here. And the pressure should be also revised to the real pressure. And we use fixed modify temperature revised to real temperature and pressure to the real pressure. Then just execute LNP in .lamps. You can get all the results.
Chuni, we have many questions on the chat. Would you like to take them now or later?
Let me see these questions.
Okay.
The distance, Alex said that the distance between, sorry,
there are many. The first one that I saw was by Pedro A. Sanchez, and starts with along with PPPM. Is there? That's the first question that you got.
Okay, along with PPPM, is there available any method for systems with slab geometry, such as electric layer correction algorithm? Sorry, I'm not very familiar with that. But you can see in our example this morning, the DPLR paper have simulated one water slab. This is the DPLR paper. You can see it simulated a water slab here. It also uses PPPM.
Chuni, there was also a question by Woodrow Wilson regarding using different types of molecules. For instance, instead of having just water, having water and say, I think he suggests a methanol. How would that work?
Do you mean this question if you have a system with multiple types of molecules?
Yes, I think that's a question.
Yes. Yeah.
How do you define which molecule is molecule one? That doesn't matter. Here we define oxygen as type 1 and hydrogen as type 2, but you can define hydrogen as type 1 and oxygen as type 2, just to give them the correct coordinates.
Okay, gotcha. I guess the part where I'm confused. So I've got like specifying the different atom types, but the keyword in your input file, model underscore charge underscore map. What I got, and maybe I'm just misunderstanding it. So is that what you put for what the charge, if you were to add up the charge on all of your Wiener centers would be? Because what's in the example is -8, but if you do it for methanol, it would be different. And if you had water and methanol, that's the part where I'm a little bit confused.
Yeah, you should revise that if you change the atom type. Here, our 1-year centroid is predicted based on the relative position of the 1-year centroid with respect to the oxygen atom. So we associate the virtual atom with the oxygen atom. So we give it 1 and 3. But if you associate if your 1-year deep 1-year model is predicted with respect to the hydrogen atom, you can do that. So we need to change it here, and also everywhere including the import here. Does that clear?
Maybe we can have a conversation offline.
Okay.
But yeah, thank you.
Another question is from Ellie. Can you comment how to set EWARD beta and EWARD H values for other systems? I don't have experience on other systems. However, for liquid water, we have a very good test in the DPLR paper. It's here. Here the x-axis is the beta and the y-axis is the arrow, and we can see the most small arrow appears here. The beta equals to 0.4, and this is for water, and I believe other systems will not differ a lot. You can test it yourself using the difference between DP and DFT. Another question is from I don't know how to pronounce the name, sorry. The problem is what is in dipole.pb. Dipole.pb is the deep linear neural network model. In our last session, the tutorial session for deep linear, we have introduced how to get the dipole.pb. We train the linear.
I've already answered that question.
Okay. Thank you. Another question is from Andrew. How big should be the database for training DPLR model with respect to the database used to train a DP model? You can use the same training data. If you already have a data set for the DP model, what you need to do is just to calculate the 1 year centroid using 1 year 19 and then train the DP model, just using the same database. Another question is, can you define different types of coexisting virtual alters having different 1 year centroid at the same time? Yes, if we have different types of 1 year centroid, for example, if we have, let me get another slide here. Here we have H2O. Oh, sorry, I didn't share the screen. Here we have H2O, and type 1 is the oxygen atom, and type 2 is the hydrogen atom. And for each water molecule, we associate the hydrogen atom to a virtual atom type 3. virtual atom, and you can find here. We have bond associate type 1 with type 3, and these two types of atoms has a virtual bond named type 1. If we also have other one-year centroid like that, we have type 4. If it's the sodium chloride solution, that will be type 5. Chloride, and the sodium will have a type, its virtual atom is type like 6, and the virtual bond is type 2. And the chloride has a virtual bond type 7, virtual bond type 3, and you just need to let me check my code. You can add the virtual bond here. We have type 1, 3. The virtual bond is type 1. If we have this, we can type in 4. It's type 4 and 6. And the bond type is 2. And between 5 and 7. Between 5 and 7. That is a bond type 3. And also in your import configuration here, you should add your bond name, and the virtual atom, this type will changes according to your system.
Sorry, I think I'm getting a little lost in all of the in all of the indices. So each one of your atoms and Wiener centroids, every single one of those has a atom type. And so for water, I could have an atom type of, I'll have an atom type for oxygen, one for hydrogen, and then another one for whatever its centroid is. And then for sodium chloride, I've got 2 more atom types, and then another Wiener centroid. And that's a different atom type than what the Wiener centroid was for the first one.
Yeah. No,
Okay.
the 1-year centroid, this 1-year centroid is for this 1-year centroid is for the sodium, and this 1-year centroid is for the chloride.
Okay, I see. Okay, and then these and so then each one of your bonds has its own index. Where
Yeah.
okay.
Yeah, that's very confusing, I know.
Oh, okay. I think I got it now. Thank you.
It's because the lambs don't allow us to define virtual atom, define the
Right,
one.
yeah.
So it's a hack method, and I believe that the DPLR people are talking with the LAMS people. They will improve on this.
Right, gotcha. But yeah, that helps a lot. Thank you.
I think we can now go to the break rooms.